Good day, ladies and gentlemen. You are welcome to our lecture number 8 on Mcen508 Power Electronics and Drives. This is lecture number 8, not 5, please. And in today's lecture, we'll be looking at motor control. And the devices that we call motor controllers, which are always together with what we call motor drives, they are electronics or electrical devices which are used for three main purposes: either to control the speed of the motor, or to control the torque of the motor, or the position of the motor. If we say position, we mean the position of the shaft that is moving. And these drives or these controllers in general, their function is to modify the input power which is delivered to the motor. And by modification or changing that input power, we can achieve a desired output. That is, we can achieve a desired speed if we are controlling the speed, or we can achieve desired torque or position depending on which parameter we are trying to control. And the controllers, they are in form of an integrated circuit which contains the controller and the drive circuits, and we use one to serve as our controller and our drive at the same time, and for this we said it is standalone unit. And the term motor drive or motor controller, sometimes they can be used in place of one another, that is interchangeably, because they are almost always together and their purpose is for that control of the operation of the motor. And we need to remember that we have four basic types of motors, and therefore we have four basic motor controllers and drives. We have AC, we have DC, we have servo, and we have a stepper motor. And each of them, what we do is, if we have a supply, we modify the supply to suit our condition so that it can give us a desired output. This diagram shows AC servo motor here. In the middle we have DC brushless motor, and at the right we have the stepper motor. Now let us look at these motor controllers and drives one after the other. We start with the AC. The AC motor controller and drives, they are electronics components, electronic devices, and their main function is to modify the input power. And what do we adjust in the input power? We adjust the frequency of the input power, that is with respect to AC motor. And whenever you change that frequency, you will be able to regulate your output speed or your output torque. And whenever you are making a purchase of AC motor controller, you are basically going to be given the motor that has certain specifications, and the specifications are basically given here. They will tell you the intended application for that controller, the drive operating mode, that is how the drive operates, and the motor type it will operate on, the inverter type, are we using pure sine wave, modified sine wave, or square wave, and the classification of the voltage also, that is, are you using DC, AC, or what type of voltage, and the power rating of the motor or the controller will be given also. The communication interface, that is, can we use a computer interface to control it? Do we use a standalone board to control it? The interface will be specified, and also the input and the output electrical specifications, they are part of what will be given on the data sheet of any AC motor controller you are trying to purchase. Now, the AC motor controller and drives, they are mainly used in these areas, that is, to control the speed of the pumps, or to control the speed of the fans or blowers. And they have other names. Sometimes we call them variable speed drives, or adjustable frequency drives, or AC inverters. And as I have already mentioned before, The controllers are integrated with the drive, and their function is to supply the control signal to the drive so that it can operate and give us the desired output with respect to either speeds or torque or position of the shaft. Now the second one is the DC motor controller, and the DC motor controller and drives, just like in the AC type, the function is to modify the input. And how do they do that? In the AC we have seen that we modify the frequency of the input, but here we adjust the constant or alternating current source. That is, the input can be constant source and it can be alternating current source. So we modify it to pulses. We change it into pulses of direct currents, and these pulses, they may have variable duration. That is, the duration of the pulse may vary from one pulse to another, or the frequency of the pulses, that is the number of pulses per second, can change. For instance, if you look at this waveform, you can see that the duration of this pulse is shorter than this, while this one is larger than this, and this one is larger than this. So you can have variable duration for the pulses, or you can have variable frequency for the pulses. And also, whenever you are buying DC motor controller and drives, these are the specifications. They are similar to those of AC motor controller. And this DC motor controller and drives, they are primarily used in these areas, either to control the motor speed or torque for machine tools, or for electrical vehicles, or for pumps in similar systems. And this controller, as I have mentioned, also is integrated with the drive circuit, and their function is to supply the control signal to the drive so that it can regulate the operation of the motor. The third one is the servo motor, and the servo motor controller and drives, just like in the two previous ones, it modifies the input signal. And how does it do that? In AC we have seen that we adjust the frequency. In DC we change either constant current source or alternating current source into pulses of variable duration or variable frequency. And in this case also, we adjust the constant or alternating current source into what? Pulses. And these pulses, they may have variable duration, just like in the case of DC, or variable frequency. And whenever you are buying, they will give you specifications, and they are similar to the ones we have seen previously. The servo motor controller and drives, they are used in controlling the motion, in motion control applications, like in manufacturing, in industries, and in construction environments, among other areas of applications. They are used mainly to control the speed, or to control the torque, or to control the position, repetition of what we have already mentioned earlier on. The servo motor can be driven by AC supply, and it can be driven by DC supply. And they are used in areas of machine tools, micro positioning, in robotics, in conveyors. And these servo motors, they have another name. We call them servo motor amplifiers. Then the last one, that's the number 4 among the 4, is the stepper motor. And as we defined the previous ones, the definition is similar. It is used to modify the input, and it adjusts the constant or variable or alternating current source into pulses or stepped current output. Into pulses or stepped current outputs. That is, it will take the input current, which is supposed to be either constant or alternating current, but it now change it into pulses. Those pulses, we can call them, in this case, stepped current output. And the specifications, they are just like those of AC, DC, and the servo motor. And the stepper motor, they are used in motion control, in manufacturing, and in construction environment. They are used to control the motor speeds, torque, and position. They are used in machine tools, in micro positioning, in robotics, in conveyors, which means the stepper motor and the servo motor, they are used in mostly common or similar areas. And these stepper motors, sometimes we call them step amplifiers, and they are also sometimes called, that is, their controllers are also called motor indexes. So these are the four controllers and drives for the four types of motors we have. And the motor controllers, they actually they need dedicated circuits that is used for supplying exact timing for energizing our coil, that is the coil of the motor, in order to have accurate speed regulation, in order to have accurate torque control, and to have efficiency optimization. That is, the inputs or the circuit must give exact timing in order to have accurate speed, accurate torque, and high efficiency of the system. And these motor controllers, as I've already mentioned, they are integrated form. We have a microcontroller, which is a integrated circuit, and the function of the microcontroller is to drive external high power MOSFET. Sometimes we can have internal high power MOSFETs integrated into the microcontroller, and the two main benefits of making it in form of integrated circuit, the first one is to make sure that all the complexity is moved into the integrated circuit, so that you, the user, you just take it and use it without much complexity. And it also reduces the number of external components, and whenever the number of components is reduced, the cost is also going lower. This is the advantage of making it in integrated form. Now, the most important function that is implemented by these motor controllers are the regulation of the motor speed, motor torque, and the power output. They also control the startup. That is, we don't just start motor with a direct supply from the mains. You have to pass it through a motor controller in order to give it some regular starting and protection. Another function is protection against the circuit faults and against the problems of overload. And it also helps in controlling the acceleration and deceleration profile of the motor. This is the block diagram of a simple DC motor speed controller using a thyristor. And if you look at it, we have our reference frequency, because we said by changing the frequency you can change the speed. Now we have our frequency comparator or phase comparator. Its function is to compare the value of this reference frequency and the actual speed of the motor, which is taken from this feedback sensor. And if the two are the same, it means the motor is operating as desired, so the output should be 0. So the firing angle for the operating of the thyristor will be maintained because the speed is okay. But whenever you get higher, you find that the difference between the two will be positive, and this firing angle will now reduce its output, and the thyristor will lower the speed. But if it is lower, we have a negative output, the thyristor will rise off and it will increase the speed. And this is the block diagram showing the microcontroller based motor controller. And here we have our setting the speed, which is used to programming the microcontroller. And the output of the microcontroller goes to the gate, and this gate is just like a comparator that takes the output of the microcontroller and the feedback from this comparator, which is taking its input from the H bridge, that is the actual output that drives the motor, and the reference current. Now these two are combined, and the difference is used for driving the H bridge in order to either maintain the speed of the motor or reduce the speed of the motor or increase the speed of the motor, depending on whether this output is 0. If it is 0, then the speed will be maintained. If it is positive, the speed will be reduced. It means it is higher than the set speed. And if it is negative, the speed will be increased. And this is our feedback that will sense the actual speed of the motor and deliver to the microcontroller. And here we have a MOSFET, simple DC motor controller using a MOSFET and 2 resistors and a variable resistor. Here is my input DC, which can be this my battery here, and here I have R1, which is in a potential divider with the variable resistor, that is R1 and the variable resistor. And here I have my R2, which regulates the current going to the gate of the MOSFET. So whenever I change the value by adjusting the level of resistance of this variable resistor, if I make it higher, you find that the output that is coming to the motor will be having small current, therefore the speed will reduce. If I make the resistance smaller, the current will be higher and the speed of the motor would be higher also. And here is another simple motor controller using single operational amplifier, and at the same time we use a variable resistor with two transistors. One is NPN and the other one is PNP, and in this case we can control two things. We can control the direction of the motor to drive it in either clockwise or anti-clockwise, or to change the speed. Whenever you change the value of this resistance toward the higher value, you find that the output of this operation amplifier will be high, and for this the transistor Q1 will be forward bias while Q2 will be reverse bias, in such a way that this motor will be driven in clockwise direction, and as you keep on increasing, you find that the speed in that clockwise direction will also be increasing. When you move it toward the smaller value, you find that the output of this operation amplifier will be low, so that it will be negative. Therefore Q1 will be reverse biased, it will be off, while Q2 will be on, it will drive the motor in anti-clockwise, and as you keep on reducing the value of this variable resistor, you find that the speed will be increasing in that anti-clockwise mode. So gentlemen, thank you very much. This is the end of today's lecture. As usual, I always encourage you to watch over and over again till we meet in our next lecture. Thank you.